All right, doing this problem called validate binary search tree. Given the root of a binary tree, determine if it's a valid binary search tree. So what's the definition of binary search tree? There are these three things. The left subtree of a node contains only nodes with keys less than the node's key. Right subtree contains nodes with keys greater than the node's key. Both the left and the right subtrees must also be binary search trees, right? So essentially, what it means is that for every node, I can check that, hey, my left is smaller, my right is bigger, but that's not sufficient. Additionally, the left should also be a BST and the right should also be a BST. But even that is not sufficient. You know why? Because let's say one is a BST. Let's say the subtree rooted at one is a BST and a subtree rooted at three is a BST. That does not necessarily mean two will call create a BST, because it could be that something on the right of one could be greater than two, right? So the limit of any tree has to be passed down. Like, so yes, so for this you see, two's left is smaller, two's right is bigger. If one had further childs down, then we have to ensure that while the left child can be smaller than one, the right childs are greater than one but less than two, right? So that extra condition of being less than 2 has to be passed down. Okay. So essentially, for every node, there is a limit of how much it can have, and we verify that to be the case for every node. For example, to begin with, this first root node can have any value, but after that, and okay, so what are the values that are supported? Node values is minus 2 to the power 31 and can also be equal to this. Okay. Hmm. Fair enough. So what can we do? Uh, so we keep on the limits, and then, so for example, we first valid for when we go to the left subtree of one, we validate that uh, the range becomes minus infinity to minus one, right? That's the range that it can be equal to minus infinity, or it can be equal to one. It cannot be equal to two. That's true. Or so we start with this. So we define the limits, right? So integer, and I was gonna define the limits as like the into initially. I would have initialized my limit to like minus at maximum integer, but that can be a valid node. So I have to use a hack. Maybe I'll do null. So integer uh, minimum uh, equals to, I'll use null, and max is null, right? And then I have to return is valid BST. I'll give it root, and I'll pass this min and max. And sorry about that. So, and now let's do boolean is valid BST tree node integer min and integer max. Now we'll check. Firstly, the root should belong in with min and max, right? So first thing is, if my root is null, okay, then I can just return true. Other thing is, if min is not equals to null and root dot val is less than or equal to min, then there is a problem, right? So that's another case. Return false. Other case is if max is not equals to null and If root dot val is less than or equals to max, then also there is a problem. We return false. Otherwise, we return is valid BST with root dot left. So for root dot left, min will remain the same and max will become root dot val. And the right should also be a valid BST. So is valid BST root dot right, but with the limits and the ranges would become um, root dot val to whatever the max value was, right? Okay, let's run code and we get a wrong answer. Let's see the first input 213. Okay, so we are returning false in the first case. We are returning false. So essentially, we are just returning false everywhere. That means one of these is causing problems. So if root's value is yeah, if min is null, that means you're allowed to have whatever, right? If max is null, you're allowed to have whatever. But if that's not the case, so if sorry, if min is not null, then root's value should be greater than the min value. So if it's less than or equal to min, then there's a problem. I think here is the thing. If it is greater than equal to the max, so yeah, okay, run again. Okay, submit. All right.